Yeah, so when I wrote an abstract for AGU, I kind of intentionally made it super vague. I'm not actually going to talk at all about SENEX. I'm going to talk about SOAS. Sorry, Yost. But I should first acknowledge, what? Yeah, maybe next time. First, I need to acknowledge a few people. So I was flying around on the P3 with Yost and Karsten and everyone else from SENEX. So a lot of credit goes to Claudia Mohr, who deployed the Figaro that we had developed a few months before. And I should also acknowledge Anna Lutz from Matthias Hallquist's group, who's also there helping us run it, because we did like 3 back-to-back campaigns. And funding to deploy from Joel's NSF career funding and a DOE grant that allowed us time to develop the Figaro. So let's get into it. So kind of the overarching story here is that the devil's in the details. So I'm going to kind of look at IEPOX SOA and what evidence there is for accretion reactions or oligomerization or whatever your favorite way to call it is. And we're going to investigate that with the Figaro TOF SIMS, and we're going to look for what fraction of OA is tied up in oligomer form. Specifically, we're going to focus on isoprene. Not that monoterpenes are important, but we have 10 minutes. So just a little bit of background info, what you need to know about the Figaro, and if you want details, you can look at our paper in AMT. We use a Teflon filter to collect particles. We have a blanking mechanism, which uses a secondary filter. And then we couple this to a time-of-flight mass spectrometer with a chemical ionization interface, and we use iodide ions, which result in very minimal fragmentation, a labeling method for ionizing gas phase components, and then we use a heated gas to desorb components from the aerosol. So what does this actually look like if we look at the data? So down here I'm showing you time and a desorption. So we have increasing temperature during the ramp profile, which is about 10 degrees C per minute. And then we hold it at high temperature approaching 200 degrees to just make sure that all the organic mass has kind of come off the filter. The instrument gets back to its background levels, and then we switch and go back into the gas phase. So for my talk, I'm just going to focus on the particle stuff. So while you're doing this thermal ramp, you get kind of a little bell curve here, where initially you have compounds in the particle phase sitting on the filter. You start to heat them up, their vapor pressure is going up, so you get more and more mass off. And then at the peak, you've run out of mass, and you kind of have a decay back till you have no mass left. So the idea here is that as a function of temperature, you can separate to some degree volatility, and that the area under these traces is the mass that was on the filter. And we're doing this with a high-resolution TOF, so we can separate isobaric compounds, get molecular formulas for these, and then try to think about what they actually mean. So there's a lot of lines on this plot, and this is actually from our paper. I should note that the solution that provided this data came from the Goldstein group, from Gabriel Isaacman in the field. So here what I'm showing you is a series of monoacids, and as you go this way in our plot, so higher and higher temperatures, you get longer and longer chain monoacids coming off, so separating by volatility, so the longer the chain, the lower vapor pressure with a given functional group. And if you do this with a lot of compounds, so Gabe made a solution with lots and lots of compounds, and you look at that as a function of temperature, they're pretty well correlated linearly with enthalpy of sublimation, which you can think of as basically vapor pressure. So what I need you to take away from this is that we have some sort of idea what this temperature means in terms of vapor pressure. So just to give you some reference points in case you don't like monoacids, here's a C4 tetrol in blue. So it's going to desorb at a characteristic temperature, which is about 55 degrees C. Pinic acid, if you're a monoterpene person, is kind of more out towards 60 C. And then a long chain hydroxy monoacid is going to be kind of out in the 80s, just for reference points. So we're talking about isoprene here, so I'm not going to go through the mechanism very much, but if you have IEPOX, you can take it up on aerosol and make products. And some products that we're going to take a look at are the triol, the tetrol, and this kind of dimer molecule. So intuitively, you would expect the triol to have the highest vapor pressure of these, then the tetrol, and then the dimer, right, based on the number of functional groups and the chain lengths. So we'd expect them to come off in this kind of characteristic shape, where first you get the triol off, then you get the tetrol, and then you get the dimer. Everyone okay with that? All right. So what does it actually look like in the atmosphere? So it turns out it's not actually that simple. So when we look at the desorption profile for, remember this is a high-resolution ion composition, so it's this elemental formula clustered with iodide that we're detecting. So we basically know how it's being ionized, and we know that it's this formula. What we see is we see 2 peaks. One that's coming off about 60 degrees, which is very consistent with a methyl tetrol desorbing from the aerosol. But most of the mass, most of the time, and I'll show you that later, is desorbing at a much higher temperature, which what we've learned from monoterpenes is that this is usually decomposition of a larger macromolecule. So this would imply that you have some tetrol partitioned, but most of the tetrol mass that you detect by thermal desorption techniques is probably not actually partitioned methyl tetrol. So let's investigate this a little farther so we can actually detect all these molecules. So if we put on the dimer here, the dimer peaks kind of where you might expect in the 80 to 100 degree range, but it's a very small fraction of the total. So it's about 10 times smaller than the inferred mass from the tetrol peak. So what we think maybe is happening here is we have large macromolecules, and this is just one possible example. There's probably lots of different macromolecules you can make. If you have something that looks like this and you add heat, it could either fragment like somewhere around this OO bond or this O carbon bond in the middle, or you could have some sort of intermolecular rearrangement where you pop off something that looks like a tetrol. And you're kind of left wondering, well, what happens to the rest of this molecule? And it just so happens that the next composition that you get, if you kind of subtract all the carbons in the hydroxy groups, is that you're going to get a C5 molecule that has a composition consistent with the triol. And the triol, if you look at the desorption profile, comes off exactly at the same time as the big peak in the tetrol signal. So what we're kind of arguing is you would expect the triol to come off before 60 degrees, but it doesn't. It comes off at the exact same time as this other peak that we think is also a fragment from macromolecules. And so this kind of gives us a possible explanation for how these kinds of things go. But I'm not trying to say that this is for sure what's happening, but an analogous process. And so then if you look at these masses correlated in time in our instrument, they're actually very correlated, more correlated than most masses in our instrument. And so this kind of, the coincidental timing in temperature space and the kind of correlation in time in terms of mass is kind of implying to us that these are co-sourced, if nothing else. So if you look at a methyl tetrol desorption, so this is another one, and you're used to looking at high-resolution mass spectra, the first thing you think of is it looks like a mass spectra. So we just adapted our fitting code for mass spectra to fit thermograms. So what we do is we come up with a characteristic desorption profile, a characteristic desorption width, all these kinds of things, so typical like resolution determinations and stuff if you're familiar with mass spectra. And we go in and we fit the thermograms using unconstrained location, but constrained width and some criteria so that peaks don't line up on top of each other. And what we do is then we can integrate these areas and get the fraction that we see as kind of a non-interacting component and something that we consider as decomposition, and we plot that up here, where blue is kind of what we would infer the actual tetrol mass to be, and the red on top of that is kind of the inferred oligomer or interacting tetrol that's in the aerosol. So what we can do is switch around. So this is the time where loadings are pretty low. They're kind of pretty apparently separable here. If I change the time, what I want you to see is that loading can change, but the thing I really want you to take away is that these locations of the peak fits, even though they're not constrained to be at the same place, they actually don't move significantly, which means that these are kind of, they're not just random locations. They're very deterministic and telling you something about the aerosol properties. And so the take-home message here is that there's a lot in the oligomer bin in our instrument. So we get a lot of data. We have a time of flight instrument. So what I've done here is just summed the thermogram for all compounds that have a carbon, hydrogen, and oxygen, and they're all clustered with an iodide, so we kind of know how they're being ionized. And if you look at the sum thermogram then, over here where these kind of green arrows are is where you would expect a peak in signal from isoprene compounds, so C5 molecules that have been oxidized, that would partition into the aerosol kind of in a non-interacting sense. So that means kind of the equilibrium partitioning kind of idea. But what we actually see is there's no discernible peak here. It's just kind of the peak shape, essentially, of what we're calling isoprene oligomers, which are kind of coming off in the 80-degree range. And then we have a secondary bump in the mean, which we attribute to compounds that have a significantly lower vapor pressure. So down here, I'm just showing you some examples, mean thermograms of the tetrol, where we have some little part from actual tetrol in decomposition. And then, the focus of this talk is not monoterpenes, but we also have molecules that go up to C30 in the aerosol that we're desorbing at higher temperatures. So I'm getting kind of out of time here, but what I want to point out is that we've got 2 peaks that we can also fit in the sum thermogram, and if I plot that time series over here, so it's arbitrary units, not mass loading, because there's a lot of sensitivity determinations that still have to be done for the whole mass spectrum. But if you kind of take this as the kind of isoprene, oligomer, or isoprene interacting compounds and lower volatility than that, you get this kind of time series where you see that there's so little semi-volatile, we think, partitioning to the aerosol that it's actually not really apparent in the sum thermograms. So we would infer then that aerosol is dominated by oligomers and very low volatility compounds. And so if you're not used to thermograms, so if you take nothing else away, what I'm trying to say is that based on compositions that have been detected, so like tetraols, triols, you'd expect vapor pressures that are quite high, tailing off at lower vapor pressures because you're starting with a C5 backbone. But in fact, what our instrument's suggesting is that you have very little semi-volatile kind of compounds, and that the volatility distribution is probably shifted, between 2 and 4 orders of magnitude lower than you might expect based on isoprene oxidation products that have been measured. So to summarize, we've got our instrument telling us that the volatility of SOA from C5 compounds is lower than we'd expect, primarily because we think oligomerization is quite important. Thermograms are kind of a way to separate out kind of direct partitioning and decomposition products, and our instrument for sure would suggest that we have a lot of oligomers present in SOA at SOAS. So there I'll end, and happy to take any questions. How do we, sorry, say that, the last part one more time? So iodide actually helps a lot with that because everything has at least one iodide. So in that sense, if you think about general ionization, you have ionization of compounds that have CHO, so their mass defect's all going to be on average probably positive. Iodide allows you to separate that to some degree in that everything's basically shifted to a negative mass defect, so the number of compounds that are actually there is fewer, but you're right, like at high mass you start to get into some issues where, is this a C18 or a C19 compound? And I'd argue for the volatility analysis it actually doesn't really matter because it's so low volatility that it's not coming out of the aerosol. But your point about the thermograms is it's a good one. So we can never rule out formation when we add heat. So I'm showing you here is a monoterpene system from a chamber experiment. And what I'm showing you here, so this is alpha pinene analysis over here. We add seed. So these are the same experiments that Mikael N's Nature paper is based on, or at least the same campaign. So over here, rose analysis, add seed again, turn on the lights. And what I want you to take away is that here we're looking at one composition, we're adding heat the exact same way. The only thing that's changing between over here and over here is that we have photolysis going on, OH oxidation, and actually the thermogram for this composition, which is actually pinic acid, changes not because we just have pinic acid and we're adding heat, but it's telling you something about the physical properties of the aerosol. So the only difference between here is what is going down. And so if we were making these oligomers just solely based on heat and having compounds around, we would expect actually way more formed over here because the pinic acid concentration spikes. So because this is telling us, at least in the alpha pinene system, something about the physical properties of the aerosol, we think it's probably telling us a very similar thing for SOAS.
Any more questions?
Yeah.
Along the same lines, you did put your tetrol in your system to verify that it did not polymerize.
Yeah, so we don't see the so we haven't done it with the C5 tetrol. We did it with the C4 tetrol that was in the solution that Gabe gave us at SOAS, but we now have an authentic standard from Jason Surratt that we're going to put in and see how that looks. The only thing I forgot to say is that the tetrol is not the only compound that does this. So, methylglyceric acid, which actually Sergey's group with some people at PNNL. They've seen these building blocks of methylglyceric acid. We see a very similar picture from SOAS, even though methylglyceric acid concentrations are actually quite low. So the idea here is that you have building blocks that can make oligomers coming from isoprene oxidation.
One more, Alan?
6 seconds. Yeah.
That was a great talk, great exciting. Did you ever see a situation where the methyl tetrals clearly dominated?
Yeah, so there are times, if I shoot back. So at the beginning of the campaign, we've got pretty high relative blue fraction here. And this kind of building up here, we have significant blue fraction. But I think, if you look at the campaign average, so it would be interesting to look with your instrument with the tag and look at kind of comparisons here. But the sum of the tetrol, which the tag presumably is measuring in a very similar way, actually agree really well in terms of time and concentrations. So we think this is definitely tetrol, and there's obviously more work to be done here, but the implication here is that we have very low volatility compounds in the aerosol.
Thank you.
Yep.